the dependence of rate on concentration. See, now we know what exactly is the rate of the reaction is and how it can be expressed. But the two methods which we have discussed, which are called average rate of the reaction and instantaneous rate of the reaction, they cannot be used to give or to have the expression for the rate for whole of the reaction, or which can be used for the complete reaction. In other words, I can say it like this, that we cannot find out the overall rate of the reaction by the methods like average rate of the reaction or instantaneous reaction. So we were always in search of the new methods from which we can find out the rate of the overall reaction. In the meantime, we also came to know that it is the concentration which plays a very important role in deciding the rate of the reaction. So that is why basically in this topic of dependence of rate on concentration, we will be studying that how the rate depends on the concentration. And in this process, we came to know about the third type of method of finding out the rate of the reaction, which is called rate law. This rate law helps us to find out the rate of the reaction, which mainly depends on the concentration of the reactants. Now, this rate law for a reaction like a reaction in which A moles of A reacts with B moles of B to form C moles of C and D moles of D, this rate law is defined as the rate of reaction is directly proportional to the molar concentration of reactants raised to the power coefficients obtained experimentally. So this rate law states that the rate of a reaction is directly proportional to the product of molar concentration of the reactant raised to the power coefficients obtained experimentally. So how it can be written in terms of formula is like this, that according to this rate law, therefore rate of reaction will be proportional to the product of molar concentration of the reactants raised to the power the coefficients like alpha and beta which are obtained experimentally. So what are this alpha and beta are? These are coefficients obtained experimentally. See, this is most important to note that basically this rate law is a modified version of the law of mass action, in which we used to believe that the rate of a reaction is directly proportional to the product of the molar concentration of the reactant raised to the power their stoichiometric coefficients. Because by that law we used to believe that whole of the reactants A and B is going to react, or all the molecules of the reactants of A and B is going to react at one time, but that doesn't happen. What happens is only a small portion of the A and a small portion of B, or some molecules of A and some molecules of B were able to react at one time. Others are not having the sufficient energies to react, and that is why when we supply more of the heat or increases the temperature, more of the reactant molecules are able to react, and that is why the rate of the reaction increases with temperature. But what is important to notice from this law is that what is the basic benefit of this law is that we know that the rate basically depends upon the concentration of the reactants. The more you take, the higher will be the rate of the reaction. So here A and B are your concentration of the reactants. And raised to the power alpha and beta are the coefficients which can only be obtained experimentally. So there is one more thing which is important to note about this rate law is that this rate law is also called initial rate method of finding out the rate of the reaction. Because why? Why initial rate method? Because it is giving us the rate of the reaction at initial time. When the time was 0, whatever the concentration we were having A and B, that has been taken into this. So the rate which we are getting is the initial rate of the reaction. So this is what was one of the methods of finding out the rate, and this is how we say that the rate varies with concentration. It's not directly proportional or square of this. It's proportional to a coefficient which is always obtained experimentally. So we do experiments and then we find out. So nobody can tell you that what exactly this coefficient is, or you cannot determine out from a stoichiometrically balanced equation what would be this coefficient. It is always obtained experimentally. There is one more important thing. The proportionality is obtained is opened by the constant. So this expression is written as rate is equal to k a to the power alpha and b to the power beta, where this k is called rate constant. We will study about this rate constant later on now, but first we need to understand this is how we express this. We write down the rate in terms of the concentration of the reactants and the product, and this way of writing down the rate of the reaction is called, remember, rate expression, which says how it is expressed on so it is expressed in this way in terms of the concentration of the reactants and the products. There is another important term which was given simultaneously along with the rate law, which is called order of the reaction. Let us understand this along with this rate law. Like suppose, let us take the same example in which A moles of A reacts with B moles of B to give you C moles of C and D moles of D. We need to understand one very basic thing, that there is another term which is given which is called order of reaction. Now you need to know what is this order of reaction is. See, order of a reaction, basically it is the sum of the experimental coefficients of reactants in the rate law expression. So the rate expression which we write down in terms of, or as per the rate law, whatever the coefficients we are having, the order is the sum of these coefficients. So order of a reaction, therefore order of reaction will be equal to alpha plus beta. And remember, what exactly this order is? See, remember, this order of a reaction is the number or the amount of the reactants on which the rate of the reaction actually depends. So there can be reactions in which there are 3 or 4 reactants involved, but practically when we do the experiment, we came to know that, or we find that it is only the 2 reactants on which the rate of the reaction depends, rest are useless. So we say that such a reaction is having an order 2. So it is basically the number of reactants on whose concentration the rate of the reaction actually depends, and or how much is the reactants amount on which the rate of the reaction actually depends. So this term gives us a very valuable information. But what is important to note is that this term order can only be therefore determined experimentally, because it is the sum of the coefficients, experimental coefficients, which are obtained in or which are written in a rate law expression. So it can only be determined experimentally, and nobody can ask you a question like that, what will be the order of a reaction? Can you find out the order of a reaction from a balanced chemical equation? No, that's not possible, because it is always determined experimentally. It can be the sum of the alpha beta can be similar to the sum of the coefficients which we are getting from the balanced equation. It can be in some cases, but as such it is only determined experimentally. Now let us study more about this order of the reaction. See, order of a reaction, which is the sum of this alpha and beta, this order of reaction, it can be 0 or 1 or 2 or 3 or even a fraction. It can be a fraction also, because we don't know anything about this. It can come out to be any figure because it is only obtained experimentally. Now let us see the rate constant. Let us understand the rate constant first. But before moving into this, let us take certain examples of the different order of reactions so that we can understand this. Let us take the example of nitrogen dinitrogen pentoxide, which on heating decomposes to give 4 of NO2 molecules and this O2 molecule. See, remember, the order of this reaction in terms of the law of mass action or the stoichiometric coefficients, if we say, is appearing to be what? 2, because we are involving 2 moles of N2O5. So if we believe that whole of these are reacting, it will be 2. But remember, experimentally we find that the order of this reaction is 1. So the rate expression of this reaction as per the rate law will be what? That the rate will be equal to K concentration of N2O5 1. So this will be this rate expression. Let us take one more example. The other example can be like when NO2 reacts with fluorine molecule, we get NO2F, and this is how it can be balanced. Now, the order of this reaction as per the stoichiometric values is 2 plus 1, which makes it a reaction with 3 order or order 3. Now, but what we find experimentally is that its order is 2, and what we write down therefore in the rate expression as per the rate law is it's K, it's NO2 to the power 1 and it's F2 to the power 1. So what we find is it is actually directly proportional to the concentration of A, and NO2 directly proportional to the concentration of F2. Total it comes out to be 2, and it's a second order reaction. So we can get many examples, like I can give you one more example, the decomposition of acetaldehyde on heating, which gives methane and carbon monoxide. The order of this reaction as per the stoichiometric comes out to be 1, because 1 molecule of acetaldehyde is involved. But what we find experimentally is that its order is 1.5. It's a fraction. So the order can come out to be any number, it can be even fraction, it can be 0, because it is obtained experimentally. But yes, it gives us a lot of information regarding the on what all amount of the reactants are involved in the reaction or are playing important role in determining the rate of the reaction. Okay? So after understanding all these basic from these 2-3 examples, now let us study the rate constant and what will be its unit from the rate expressions.